Um, okay, so let me begin then. So today we are very happy to have Onirban Islam. He did his PhD from Leeds University and is currently a postdoc at Potsdam University at the Institute of Math. He works on general areas of mathematical physics, including entanglement entropy, and today he's going to tell us about entanglement and von Neumann algebras. Take it away, Onirban. Thank you.
Thank you very much for the kind introduction. And yeah, as announced, I'm going to talk about entanglement and somehow related or may not be related at priori, some mathematical ideas due to von Neumann, of course. So let me straight go to the main theme of the school is a school on quantum field theory. And one of the reasons that we are having this school on quantum field theory is apparently these three apparatus. So first one is a replica, which Rutherford used to discover electron. And next one was the best before the third large hadron collider in CERN, so Tevatron. So this is responsible for some of our fundamental understanding about nature. For instance, quark was first detected here. On the other hand, I think CERN LHC is well known for most of you. Lots of important discovery has been found here. For instance, Higgs, the latest one. Now, as we have already seen, the first part, or first word in my title, is due to Schrödinger, who coined this word entanglement. He wrote quite a few influential papers, and one of his course goes like that. I would not call entanglement one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So in this talk, we will explore what is this characteristic trait, entanglement, and keep in mind these three amazing tools or apparatus in human history, which helped us to understand nature. And we will use something analogous of these three tools. And let me call this tool for the time being Von-Neumann algebras. And as this picture shows, from left to right, the right we are getting more precise understanding of nature. Like these three, we will also have three types of Von-Neumann algebra. And the more final classification we will get more precise understanding about entanglement. So let me give an idea of the content of this talk. So let's say we have two subsystems, which are quantum mechanical, can be quantum field theoretic, can be quantum mechanical, doesn't matter. And we have the combined system. So then we ask, what is the states of the combined system? Of course, you can take one state from one system, another system, and then just tensor product, and this gives you product state. So entanglement comes from the question, take any state on the combined system, can you write it as a convex combination of product states? And the answer is no. How do we know? That comes from historically Einstein, Rodel, and Podolsky, this famous EPR paper. And lots of paper in between. One of the landmark work is by Bell, who also constructed an entangled state and showed that this is not only philosophically or fundamentally important, rather it has experimentable consequences. So this experiment started with mostly Alan Aspects and his group. He performed several experiments in 1980s, in particular this three paper, where more or less he showed that Bell's inequality is violated. However, there was some loopholes in his experiment, mostly due to technical reasons. And since then, people try to improve this situation. And in 2015, two groups independently, Henson and Guistina, they more or less settled down issue. Entanglement is true, Bell's inequality is violated. It also solves some of the other contemporary theories and interpretations. And since then, people are trying to refine these things in a precise way. So these are some more interesting results. Some are from this third picture we have shown, this Atlas and CMS collaboration. And now we ask this question, all right. So if someone gives me a state and asks, is it entangled or not? So in general, we cannot just take violation of Bell's inequality because all these states are not Bell's state. So we want something which can measure entanglement, and that's called entanglement measure. So you feed a state, and if it gives 0, then it's a separable state, no entanglement. And if it is get non-zero, then there is some entanglement. And the more number, the better entanglement, or more entangled the systems are. It also needs to satisfy at least one fundamental in the sense that everyone agrees that this should not increase under local operation and classical communication because all our experiments are local. So these are quantum experiment. On the other hand, once we have experiment, I can take a cell phone and then call Nabil Iqbal or Rakin and say, I got this result. And if I do that, I cannot create entanglement. Okay, so what nature gives us, that's one, but I can just tell. And there are many. For instance, you can look this review by Vidral and from information theory perspective, Plenio and Veremani, and in quantum field theory, Hollands and Sanders, like what are others conditions required. So I'm not going to details, that's not important. Just we need a tool where you fit state and it will give us how much is entangled, if it is entangled at all. There are many entanglement measure. We started with violation of Bell's inequality, Von-Neumann entropy of entanglement, entanglement distillation, relative entanglement entropy, mutual information, and whatnot. Now we question, okay, what we use. So it's always a matter which is good and bad. And apparently, Vidral in the realm of quantum mechanics and quantum informatics showed that relative entanglement entropy, something I will define and discuss later, is a good entanglement measure. Means that you take quantum mechanical system or quantum field theoretic system, it can detect entanglement very well and satisfy this more and less expected properties. However, apart from this fundamental understanding, entanglement has phenomenological aspect. For instance, there are proposals that it may explain black hole entropy. You can look at this review article by Solodokhin and Martinez and Minucci. In condensed matter physics, there are proposals that it may be used as a non-thermal order parameter. You can also look this review article by Izard and his group and Laffericci.
There is a question. Do you want to take it now or later?
Sure.
Okay. So what does it mean to have entanglement measure equal to infinity? Any example of such cases?
We will see. Thanks for the good question. What does it really mean? All right, and then now it's a huge business, quantum computing and informatics. You can also look this review article by Vidral and more recent one, Hroditsky. However, due to time constraint, I'm not going to talk anything about this phenomenological aspect, which are very interesting. But I just want to give a glimpse what this entanglement measure, this relative entanglement entropy can give us. So if you consider two subsystems which are very close, okay, almost touching to each other, we'll see more precisely what does it mean. Then it shows something called area law, which means that if you take a subsystem and it scales like the area of subsystem. Look, this is different from thermodynamic entropy, where you have a volume law. Okay, that's a fundamental difference. You can also say, how about the subsystem are very far from each other? For instance, one side of a black hole, and we are maybe doing experiment from Earth. Then it shows exponential decay for bipartite system proven by Hollands, myself, and Sanders. So in this talk, I'll be mostly explaining what is entanglement and how pre-operators like the beautiful machines can help us to understand that. And if time permits, a bit about this area law and exponential decay. So let me first recall a formalism. I think in this school, we learned this formalism due to Heisenberg and Schrödinger. However, there is another formalism in quantum mechanics due to Von-Neumann, and that seems very important for our case. So let me just recall a bit. So we consider in quantum mechanics a system of finite many degrees of freedom. So we have a Hilbert space, always separable, so I'm not speak about it anymore. And then this is isomorphic to Cn. And a density matrix is a matrix which is positive and trace is 1. It's introduced by Von-Neumann and then less systematically by Landau. And the expectation value is just trace of density matrix on some observable A. those who are not familiar, density matrix can capture pure and mixed state together. Okay, so if it is a pure state, then density matrix square equals to rho. And then due to spectral theorem, you can write this way. Usually in physics, one uses bracket notation, and this is more mathematical notation. And then it reproduces what we know for expectation value of observable with respect to a state or pure state called wave function. As an example, you take simple two-dimensional system. Then if you take a matrix with all elements 1 with half, this is the pure system or pure state, and mixed state is just diagonally 1. All right. More interesting mixed state is, you may know from statistical mechanics, like Gibbs state or thermal state, which is e to the power minus beta h, where beta is the inverse temperature and h is some Hamiltonian, which is stress class, so that it makes sense. For instance, it's a discrete spectrum. Remember, in quantum field theory, usually Gibbs state doesn't exist because it's not stress class. Okay. All right. Now let's try to understand quantum mechanics and quantum field theory. Okay, so let me start with quantum mechanics. So we just take some Hilbert space, anyway, Cn. And how do you combine system? Just do tensor product. And then observable, you take one observable and then tensor product to identity, and the other way for other system V. And independent subsystem means that you can do experiment. So you take trace of row U, A, and B independently, and you can get result. Okay, so that's the idea of product. So you can do everything independently. And that's why it has this separable state idea. So you can write as a convex combination here of two states, in this case, density matrices on subsystem U and V. So if this is possible, then these are called separable states. And if it is not separable, then it's called entangled. As an example, very well known, Bell's inequality. So you take two-dimensional system, usually it's called qubits then. So you take 0, 0, so you say you just take two eigenvalue of a spin operator and 1, 1, and then for normalization is square root 2. And you see you cannot write it in this form. Okay. But now, as I told, in general, in quantum field theory or even quantum mechanics, you can give me just an state and ask this question: is it entangled? And you can try, okay, let's try to write this way. And usually it's not very hard. It's usually impossible that you try from by definition and come up with something reasonable. So that's why we have this idea of entanglement measure. And one measure is the relative entropy, which means that you take two density matrices and you compare between that. So it's stress rho log rho minus rho log rho tilde. So you take two states, okay? So you are not computing entanglement or entropy for one state, rather you are comparing to state. So as the interpretation, you can think, okay, we have information about the state rho, and if we update our system to rho tilde, then how much information we gain or loss, whatever, okay? That's what relative entropy says. And this is a generalization of the usual Von-Neumann entropy, okay? And now we want to have entanglement. So what we have to do, okay, we take relative entropy and just take infimum with respect to all separable states. Then it gives us how much this is entangled. If it gets 0, then it means that both states are separable, right? There's only possibility to get 0. And then this is 0. And now if it's infimum, it may be infinite. So what does infinity mean? Already asked, and we will see, okay? Now, let's just try to imitate everything in quantum field theory. So in quantum field theory, our subsystem are space-time localization. So let's consider U and its surrounding U prime. Now we know that for simple situation, it's a Fock space and this is infinite dimensional, but then this is no more isomorphic to Cn. So question is that how do we choose this state or the space of states? Because you see, this is very crucial. In quantum mechanics, we know it's Cn. So it doesn't matter what you are doing, but this is no more Cn. So you have to tell which one. Okay, now what we need some density matrix to do what we have in the left-hand side. Unfortunately, in general, density matrix doesn't exist in quantum field theory. Okay, so what can we do? Maybe we can try wave function approach. So we try to localize using wave function. But in general, a wave function is not a localized object, it's a global object, right? You have plane waves, it's everywhere. You can say, okay, how about we take wave packet? Okay, so we construct a wave packet in the red region, and maybe that's why we can describe our subsystem. There is two problems. First is that if you consider time-dependent system, even if you make a localization at certain time, with time evolution, this localization might be destroyed. You can say, okay, that's complicated. I just happy with time-independent system. Then comes more fundamental reason, something called Rich-Leader theorem. It tells that you take any state, for instance, some nice state, for instance, vacuum state in the red region, and then you act with some local observable. Local means observable which is only knows about the red part, and you act because we need to have expectation value, right? So in quantum mechanics, you will get Hilbert space only in the red region. But Ree and Schlieder proved in quantum field theory, you get entire Hilbert space. So you cannot keep localization. So using wave function as a localization tool is not really going to work. Well, then how about our usual notion that if you have commute, then we can just have subsystem? It's not going to work. And if that's not going to work, how we define relative entropy and relative entanglement entropy? And that's the part we will explore. So the idea comes from the people on the left-hand side, Araki, who used algebraic formalism due to Haag. And Haag's idea is kind of opposite of Dirac's idea, one of the founding father of, say, quantum field theory. So what Dirac told us, we have Poisson algebra, and we deform it to a commutator algebra. And Haag took this algebraic idea very profoundly, so algebraic formalism. But instead of starting from a classical algebra, he said, okay, we start from inherently quantum algebra, and then we take semi-classical limit, and we should reproduce it. So from the very onset of this problem, we want to do it in a quantum way. So how it works? Let me first recall some vocabulary. What is an algebra? An algebra over some vector space R or C is a vector space, and which has the product, which usually we just write A, B, which is associative and distributive. It is called abelian if this product commutes. And we define something called involution map, which is a map from algebra to algebra, which A star star equals to A plus B is A, convolution is A star plus B star. And if you take product, then B star times A star. And if you have some number, then you just have complex conjugation, okay? And let me also recall what is a norm. Norm is a map from algebra to non-negative numbers, which satisfy these properties. Like if it is 0, then the element is itself 0. And then we have multiplication, like lambda times A. Norm is absolute value of lambda times norm of A. And then we have triangular equality and multiplication inequality. Now we define something called C-star algebra, which is a triplet, if you want, which is an algebra endowed with an involution and norm such that norm of A star is A, and A star product A is norm of A square. Okay, maybe too abstract. Let me remind about matrix. For matrix, involution is nothing rather conjugation, okay? We do matrix transpose and all these things. And norm, you just take matrix norm. So this is an example of C-star algebra. Maybe a bit more. So we consider Hilbert space and operators on the Hilbert space such that which is bounded in operator norm. Recall operator norm is a supremum over an operator acting on the element, which that elements are normalized. In general, it may or may not be infinity. If it is less than infinity, then it's called bounded operator. One can check, it satisfies all this property, and this is also an example of C-star algebra. Now, the name of one of the words in my talk is Von-Neumann algebra, and to define it, we need to have this notion of commutant. So we consider a subalgebra of bounded algebra over a Hilbert space, and commutant is all elements which commutes with A, okay? So remember, we will need this terminology. Commutant is nothing but just element which commutes the element. Okay? And then Von-Neumann algebra is something R, which is equals to double commutant. So you take R and then you take another R prime. If they equals, then it's called Von-Neumann algebra. If you are not familiar, it may be very abstract. Then just remember, Von-Neumann algebra is something which satisfies some properties. All right. Question is that how these things are going to help us. We will see shortly. Now we back come to the Huck's philosophy. Huck's idea is that we are living in a space-time, and then quantum objects are living on a space-time. So, and as an experimentalist, we can only probe finite region of space-time. So we associate some observable on our finite region of space-time in a nice geometric properties. And then we collect the net of all observables. And our observation is that they constitute some algebra. For instance, in quantum mechanics, PQ has this commutation property, which is Heisenberg algebra. We have algebra of commutation relations, algebra of anti-commutation relations. So that means some algebra, all right? And then once we have, any question?
Yeah, there's a question in the chat. I also had the same question. What did you mean by double commutant?
Double commutant? Just you take commutant of R, then you get R prime, and now you take commutant of R prime. Okay, thanks for the question. So once you have the local algebra, you want to consider a total all over space-time. So you just take closure, take the union, and close with norm topology, okay? Once you have algebra, then we need state because we want to do experiment and we measure correlation function. And a state is a map from algebra to some number because experiment we get some numbers. And we have always get positive numbers. So it's a positive map in the sense of C-star algebra and it's normalized. So if you get one element, then it will get one. Question is that how it relates what we know so far from Hilbert space. And that's given by the Gelfand-Naimark-Siegel GNS theorem. So it tells us that once you have an algebraic state, you can get free. You don't need to do anything. A Hilbert space, infinite dimensional in general setting, star representation of algebra as a bounded operator on this Hilbert space. We have already seen what is the bounded operators and a GNS vector, which is norm 1. Okay, and how it relates? So expectation value of an observable A, omega A, is nothing but the representation of that observable on the Hilbert space and taking the Hilbert space product with the GNS vector. Now, remember, that's the beginning point of somehow the quantum mechanics or quantum field theory. So the right-hand side is expectation value in the Hilbert space approach, and left-hand side is the algebraic approach. So that's how the two matches. As an example, if you take Minkowski space-time and the vacuum state, then F is just a Fock space, and omega is just the vacuum vector. So this may be more familiar, like 0 vacuum vector sandwich some operator, okay? So now, hopefully, more or less it's clear that if you are doing algebraic approach, you can always come to Hilbert space approach, and Hilbert space approach it just comes from as a special, not a special case, as a derivative of algebraic approach from the GNS theorem. All right, now let me give a concrete example. In this school, we have seen quantization of scalars and fermions. So I just pick fermions. So we take a time slice, and then we have equal commutation anti-commutation relation, this one. Now, if you look at closely, you see there are at least problem. Because in our usual setting, we say psi is an operator. Now, when you say an operator, you have to say in which Hilbert space. That's the definition of operator. And since this is infinite dimensional Hilbert space, you have to literally tell it. It's not just some Cn. On the right-hand side, delta, and delta is not a function, rather it's a distribution. So in some sense, we are writing an equation, which is operator equals to distribution times identity operator. So if you really care about mathematics, this equation cannot be right. Okay. So one idea is to get rid of this, that let's first take care of the distribution. And if you look at Dirac's book, Dirac tells us whenever you have Dirac delta, you will always integrate. So let's do it. Now it's a spinor, so you cannot just integrate. You have to pair with spinor and co-spinor pairing, and that I give this psi k. So loosely speaking, this means you just smeared with compactly supported spinors. All right. More precisely, we need square integrability, right? We want to have expectation value. So we consider co-spinors of a square interval. So it's L2 space over the Cauchy hypersurface, or in this case, R d minus 1. And we can do also for spinors. I denoted by L for spinors and K for co-spinors. Okay. Now the operator problem still remains. And one way to resolve these things, you consider this algebra as a distribution. Okay, we forgot about operator because right hand side the distribution, maybe everything is nice as the distribution. What does it mean? So we consider free unital C-star algebra. At least you see C-star algebra means something we have seen, generated by the symbols. So if you're not familiar with terminology, just think that it is some algebra which is generated by identity psi k, which means something like this, and psi k prime as this will be psi star k prime modulo this relation, and that is precisely a mathematical version of canonical anti-computational relation, and that is called R algebra, if you like. Okay, and now there is no mathematical problem. Everything is well defined. Now you can ask, okay, but how we go back, because we know Hilbert space approach works, and how we get back. We have seen already a sketch. Now let's see it with more detail. So in the algebraic approach, quantum fields are distribution on some algebra. In this case, here R algebra.
I'm sorry, probably I missed. How are you defining the co-spinor?
It's just dual bundle in the spinor case. So you have a spinor bundle, and then you have dual bundle.
Okay.
Okay, and now we need observable algebra. Remember, fermionic field is not an observable, but even combination or bilinear combination is observable. So we just take bilinear even number of, okay? So this is a sub-algebra of the field algebra. However, for entanglement, we see we need localized system. So we need local algebra, which means that you do same thing, but now your support is only in some local region. And then you have local observable algebra. All right, now we have algebra. Now we need a state, right? For quantum field theory, we need both things, algebra and a state. So let's take vacuum state. And this is just what is vacuum? Is a unique pure Gaussian state, which is invariant under Poincare group. And usually this definition is given, that is a ground state with respect to time evolution, means that it is the lowest energy eigenstate. But this definition is not a good definition because energy is not a relativistic invariant quantity. So if you use this definition, it's highly frame dependent, all right? And now we come to GNS representation. So GNS tells that we have a fog vacuum, that is what we know, and one particle Hilbert space, and from one particle Hilbert space, we cook up Fock space. And then last line is basically what we usually do in Hilbert space approach. This is the field operator represented on a vector space. This vector space is explicit which vector space, and I is a mapping from the L2 spinors to this one particle Hilbert space. Now look the difference. In the algebraic approach, in general, fields are distributions, not operator. They become operator only when we take this representation. So operator comes as a secondary step. They are not fundamental. All right. And then we take the double commutate of the representation. So now instead of this only field, you take representation of the whole algebra, local algebra, and you take double commutate. And due to some general theorem, this is just Von-Neumann algebra. All right. So we have our Von-Neumann algebra. Why this is interesting? So before going there, let me recap. Quantum fields are not necessarily observables. And local algebras are Von-Neumann algebra, can be given this structure. And quantum states are global object. However, observables can be local. And in general, they are local. Okay, so let us now combine this abstract algebraic setting to quantum physics, what it has to do with entanglement. And we will see these three people has contributed enormously in this field. So let me have some dictionary first. So let's we have some Von-Neumann algebra. We have seen how it arises, but now forget how it arises. Just take any Von-Neumann algebra. A center is called, you take Von-Neumann algebra R intersection with R commutant. This is called center. And R is called a factor if its center is just identity. Okay. Why these are interesting? We'll see shortly. I recall a projection is an element of algebra which is square equals to itself and which is a self-adjoint. This is called projection. This is called abelian if projection on this algebra is abelian. We have seen what is an abelian algebra by far. Two projections, E and F, are called equivalent, given by this symbol if there exists an element of this algebra such that E can be written as W star W and F can be written W W star. Okay. And E is called infinite if there exists a projection F such that E is equivalent to F, but they are not, but F is less than E. And if it is not, then it's called finite. And E is called central projection in the Von-Neumann algebra R if E is a projection on the center of this algebra. So I understand lots of terminology, why it is useful. Now come to the analogy of standard model. So what does the standard model gives us? It tells that whatever we see can be reduced up to some sense, some fundamental quantum fields. So quantum fields are right now, as effective field theory, are building block of our nature. So to understand, we just need to understand the building blocks, and then we can build up our universe. You can have the same question in the sense of algebra. Can we get every Von-Neumann algebra from some building blocks? And the answer is yes. You can write as a direct sum or integral, depending on situation, as a factor. And that's why we define what is a factor. And how it looks like? So Murray and Von-Neumann tells a Von-Neumann algebra is called type 1 factor if it is abelian. What is abelian is written here. And its smallest central projection is just identity. Well, you can have type 2. It means that no abelian projector, but we have only finite projection, which means that this is not satisfied. And of course, smallest central projection is identity. And type 3, which is none of this. Okay, why has something to do with this abstract nonsense? Hopefully now this is tempting. It turns out that whatever we encounter in usual quantum mechanics, I will come more precise later, is actually a type 1 Von-Neumann algebra in this classification. So if you are a mathematician and you don't want to learn quantum mechanics, you can say, okay, I just learned type 1 Von-Neumann algebra, and then not all Von-Neumann type 1 Von-Neumann algebra has something to do with quantum physics, but quantum mechanics is a part of type 1. All right. How about type 2? Some quantum mechanics and some quantum field theory. I will give explicit answer later. And the type 3, people thought it's too exotic, even mathematicians, and they thought there will be never an application of type 3. Even Von-Neumann didn't expect it. However, Araki, we show his picture beginning, showed that if you consider a non-relativistic Bose gas in finite temperature in infinite extended situation, this is an example of type 3. So one of the earliest example of type 3 Von-Neumann algebra was actually constructed from quantum field theoretic model, a non-relativistic quantum field theoretic model. And that really was very counterintuitive and also ignite the further research in this classification. Now remember, we have 3 machines. First, we have this cathode ray tube, which can only tell something. So you can think this classification as an analog of this first Rutherford. And later we have Tevatron, which is more finer, gives us quark. So now we want a finer one, okay? Even more precise than this. To do that, I need some more terminology. So something is called a weight, which means you take non-negative elements of algebra and it will give 0 and infinity included, okay? Which is linear in this sense. And if you have some number, it just comes up before. So also linear in number. And it is called a tracial state or weight if it is a weight which satisfies A star. So trace of A star A is equals to trace of A star. So if you consider matrix, you know, trace of AB is same as trace of BA. This is a generalization of that idea. But in general, for infinite dimensional matrix, this is not true. But this is more general because this is also true for infinite dimensional algebras. And that's why we have this notion. All right, and now again, we consider projections. We have seen already projections are useful. Now, something analogous to Tevatron. Before we have only type 1. And now, Murray and Von-Neumann shows if we take the range of a trace restricted on some projection, on any projection, and if it belongs to this set, then this is called type 1n. Okay, and this is called type 1 infinity if more or less similar, but now infinity is also included. All right, how about type 2? Type 2-1 if the range of the trace restricted on projection is in 0 and interval in 0 and 1, and of course not type 1 and has no non-trivial finite projections. And what is type 2 infinity you take same thing, but now from 0 to infinity. For type 3, it cannot be useful because just infinity. Again, same question, why this abstract nonsense? So type 1 is isomorphic to algebra of matrices, and that's precisely our usual quantum mechanics. So now you see we have more precise characterization. The algebra naturally arises in quantum mechanics. You can normalize it, and this normalization 1 gives basically the trace of A is our usual trace, sum of diagonal entries, all right? Because now it's finite dimensional matrix, so our usual thing should be reproduced, and it has been reproduced. Type 1 infinity, this is isomorphic to algebra of bounded operators, but on an infinite dimensional Hilbert space. In this case, the trace may or may not be finite. So type 1, some quantum field theoretic model, for instance, Chandrasekhar, Witten, Longo, they have idea this time that you can consider quantum field theory only in terms of some detector, which is motivated from some quantum gravity model and some other assumptions. And if you put sufficient assumptions, then you get actually type 2-1. If you consider quantum mechanics with a magnetic, external magnetic field, then you also get type 2-1. Okay, so this abstract nonsense gives you more precise thing, like how quantum mechanics and quantum field theory is related or different. All right, so remember we have 3 machines. So last machine was our LHC. So again, sorry, introduce more machineries, and that will be last machinery. So a vector is called separating for the Von-Neumann algebra R if for all elements of R, if you act with an element of A in R, if it is 0, then the element itself is 0. Okay, and it's called cyclic if you take any element of R, acts on the Hilbert element of Hilbert space, take the closure, then you get entire Hilbert space. If you're not familiar, forget about this, know some property. We assume this property is satisfied. We'll later see if it's true or false. And then Tomita in 1967 defined some operator. It's very hard to find Tomita's original article because it's written in Japanese and not published in a very proper journal. I think Tomita didn't really realize his potential. It was Takesaki, a fellow Japanese mathematician, who realized it and published in English. And this is a densely defined operator on R on omega to same. So you take an element acting on this cyclic and separating vector. What it does, it just gets star. You remember the involution? It just gives the involution. Function analysis tells that this is a closable operator, and then we can take polar decomposition, which is written by J square root of delta. So J is an anti-unitary operator. It's called modular conjugation. And delta is a self-adjoint non-negative operator called modular operator. So if you don't want to remember anything, everything is nonsense, then just remember red light. What is it? Something called modular operator. Let's look at our favorite example, algebra of matrices. Then and state can be identified with density matrices. Okay, so this is expectation value in quantum mechanical sense, and there's algebraic sense. We assume there is no zero eigenvalue of density matrix. Then the GNS Hilbert space is just basically matrices, Cn tensor product with Cn bar, which is just conjugation. And GNS vector is nothing but a square root of density matrix. Then the modular operator is nothing but square root of density matrix tensored minus square root of density matrix. Okay, hopefully now it is at least something concrete. Again, why we need this abstract nonsense? Let's see. So you remember we have classification of type 1 and type 2, and they're fine classification. But for type 3, we cannot do anything. And Murray and Von-Neumann, they also couldn't come up something better. Alan Cohn, in his PhD thesis, showed that if you consider a spectrum of this modular operator with respect to all faithful normal semi-finite weights, which means that these are weights which will give positive thing if your element is positive. Normal means you always have such correspondence with density matrix, and semi-finite means it can be infinite. And you take intersection over all these states, then you get something called a spectrum of modular operator. He calls it modular spectrum of a Von-Neumann algebra. Why it is useful? Remember, now we have only left with type 3, and type 3 shows up in quantum field theory. It shows that something is called type 3 lambda, where lambda is from 0 to 1 if the spectrum is 0 and lambda to the power n. It is called type 0, 3,0 if the spectrum is only 0 and 1. And it is called type 3,1 if the spectrum is non-negative real line. So this is originally due to Cohn's PhD thesis, but similar idea was by Araki, Cohn, Stormar, and also some work by Takesaki. Now comes our main message that we saw that quantum field theory, the algebras are type 3. Now, more precisely, they are type 3,1. So Friedenhagen proved in a very model independent way, if you have some natural assumptions, which usually are good in physics, then all local algebra of observables are type 3,1. And that's the reason why we are so much talking about this classification. And next, I will show how this classification will help us to understand entanglement. I just want to mention that you can also do everything in curved space-time, at least globally hyperbolic, and then this type 3,1 result also survives. All right, so take-home message for the difference between quantum mechanics and quantum field theory. Quantum mechanics type 1L algebra, quantum field theory type 3,1. So if you want to forget everything, remember our color of flag. Red is for our heart, quantum field theory, type 3,1. And our background is green, it's quantum mechanics. All right, now we come to entanglement. So if you have endured the pain of algebras, you should get some fruits. So again, we come to our space-time localization, and we have a space-time region, the red part, and then we associate an algebra. We know how to do it now. And we have a bipartite system, which means that this symbol V means that you consider U, and V can be U prime or something else. So this is basically the system generated by RU and RV, okay? Where U and V may be surrounding or not, okay? Now, if they are type 1, then their tensor product is also type 1. And then the algebra generated by RU and RV are isomorphic to the tensor product of this algebra. And that's basically what we also see in quantum mechanics, right? If you take two quantum mechanical systems, how do you combine them? You just take tensor product. However, in quantum field theory, we have type 3,1, in fact, type 3. How about type 3? So if you consider U and its surrounding, U prime, then they do not have tensor product decomposition. What does it mean? What it means precisely the infinite entanglement. Why? Because if there is no tensor product decomposition, it means we don't have an independent subsystem. Look at this picture. If the red region is a quantum system and U is surrounding, they are touching. So they are exchanging information every time. And a very minute amount of touching or exchanging information is sufficient to destroy independent subsystem. In other words, infinite entanglement means they are not independent subsystem because they are exchanging information. And that's what it shows here. And if you look at some usual quantum field theory computation, for instance, the Scalabers-Riccardi, Cassini-Huerta, and also from string theory community, this review article by Nishioka, Ru, and Takaniagi, you will always see that entanglement entropy is something infinite plus some finite term. Why you have infinite? That's the reason. Because you start from wrong assumption. You thought they have independent subsystem. So you can also think it's some sort of an ultraviolet regulator. Because if you think philosophically, if you say, okay, two quantum systems are touching, that means that you are probing at a point-like distance. You can't do it. So this is also philosophically and fundamentally not the right idea. So what can we do? Always infinite? So operator algebra tells us, no, we can resolve this issue by precisely considering two subsystems which are not touching. So there is a safety corridor between two subsystems. So instead of U and its surrounding, you consider U and some other subsystem, V, which are causally separated. So there is no causal communication. And then the combined algebra of these two systems is isomorphic to tensor product decomposition. And this tells you have actually subsystem. And then the entanglement entropy will be always finite. something, but finite, no infinity. It also tells, remember, we don't have any density matrices, and in general, we also didn't know if we have a separable state. It also tells if this condition is satisfied, then we also have a separable state. So the result is originally due to Del Antoni and Longo in more operator algebraic setting, and Fuster prove it in a more quantum field theoretic idea and curved spacetime. Okay, now come to our definition. Remember what we start? We want to define relative entropy or relative entanglement entropy. So now we consider we have two cyclic and separating vectors, and this is satisfied in reasonable quantum field theoretic model. And then we again define Tomita operator, but now it's the relative Tomita operator because we have two states. It does the same, A goes to A star, but now it's act on two different states. Okay. Why we have two these things? Because we have now two subsystems, U and V. So one corresponds here and the corresponds there. So I think it's natural. And now you play the same game, modular operator, okay? But now it's a relative mode. Everything is relative. So I'm not going to utter this word anymore. And now Araki gives us this formula. So that's how you should define relative entropy when you have a type 3 Von-Neumann algebra. At least to me, it's very abstract. And how it related? You remember, we saw an example of modular operator for algebra of matrices. If we take that example and put everything there, it literally reproduces the relative entropy for quantum mechanics that we saw very beginning. So this also gives, maybe it's too abstract, but on the other hand, it reproduces what we already know. And that's one of the reasons why operator algebra gives you a very clean characterization, because now we are, see, localizing using the modular operator, not states. So this is also called modular localization. Okay, once we have relative operator, we play the same game for relative entanglement entropy. We take infimum over all the separable state. And when the separable state exists, we also see that when this tensor product decomposition exists. So in a way, this Von-Neumann algebra classification in a one punch tells when entanglement is infinite and how to get something finite and what are the formulas. Okay, now we have the formulae and now we want to compute, because in physics we like to compute. So we saw the example of Dirac field. For simplicity, I took Dirac-Majorana. Okay, and it's ultrastatic, slightly general than Minkowski, which means that in R cross, instead of RD minus 1 is just some Cauchy hypersurface. So we can have curvature in a spatial direction. So we have two space-time localization, U and V, as before. If you want, so since it's ultrastatic, I can have just taken a slice, and then I have localized region. If you say, okay, I want more space-time picture, you can take this causal diamonds. Everything works fine. And now you take some finite distance, because our operator algebra tells, unless you take finite safety corridor, you are going to encounter infinities. So first we want to take, okay, there is beautiful results from standard quantum field theory we want to reproduce. So what we do not start from touching, rather we start from general distance D between subsystem U and V. And then in general, it's very hard to compute relative entanglement entropy, but we can say an upper bound of this asymptotic. So they are very close, but not touching, okay? Because again, touching means you literally know pointwise localization. Quantum field theory doesn't allow it. And operator algebra tells that even if you do it hypothetically, it's infinite. So it goes to 0. And then this very complicated formula, but what is upshot? If you take the leading order term of this formula, then you reproduce the area of this region, the area of U, and that's the famous area law. So sometimes you will hear that quantum field entanglement entropy always satisfies area law, where the thermodynamic entropy gives volume law, and I think now it's mathematically precise. What does it mean? However, it is not always true, okay? Who tells that subsystem will be always very close? We can consider a black hole in the center of Andromeda, and we can try to do some experiment from Earth in future, or maybe gravitational wave. Then you can think they are far, far apart from each other. So asymptotically infinite. And in this setting, you can also compute. So this is done with Hollands during my master thesis. And then it shows exponential decay. So entanglement entropy doesn't always show area law. In this sense, if you take this thing, you will say that it decays with the distance and effective mass, because we have considered some curvature. And you know, space-time curvature can act as a mass, and that's the scalar curvature. And mass is the usual mass we put, or particle mass in flat space limit. So the higher massive, the higher decay. Okay. All right. So by this, now I would like to just recap. So the message, if everything is very abstract, at least if you take this viewpoint of algebraic, quantum fields are net of algebras. Okay. And states are global objects. In general, entanglement is a non-local correlation. There is nothing spooky because states are anyway global object. So they have global information. On the other hand, the fundamental question, what lets Einstein, Rosen, and Podolsky, the CPR paradox, is that back then it was not clear how to formulate quantum field theory in a very proper setting. Also in quantum mechanics is inherently a non-causal theory because there is no causality in quantum mechanics. So it was not the right framework really to understand. But once we have this quantum field theory, then we can isolate what is a local aspect, what is global aspect, and we see that entanglement is just a global aspect. There is nothing spooky about it. And if you adopt this viewpoint that quantum field theory is entirely defined in terms of observables, then there is also nothing non-causal. Okay, and Von-Neumann classification helps us to distinguish between quantum mechanics and quantum field theory. In particular, for usual quantum mechanics, it's type 1n, and for very large number of model-independent quantum field theoretic model, even in curved classical space-time, this is type 3.1. And when type 3.1, you cannot just take subsystem as a tensor product because it doesn't allow us to tensor product decomposition. You need some finite safety corridor between two subsystems which are causally separated. Otherwise, you will encounter infinite entanglement. And again, you can take, at least, I mean, for computation, it depends how complicated system you are considering. For some system, you may be able to compute for general distance, but for Dirac-Majorana, it has been computed. If they are closing to each other, very close, then it's famous area law. If they are very far, then it's exponential decay. And if you want to read more, then these are some of the literature. This Clifton and Hull version is very conceptual. This entanglement and open quantum system in a KFT. And if you want to understand more about how subsystem and independence is different in relativistic quantum field theory than usual case, then Summers has a very nice review article. Unversion has written a nice book chapter on the problem of localization using wave function approach. And if you want to more about how to compute, then this book by Hollands and Sanders. And if you want to be motivated more from physics approach, then Witten has this nice review article. So with this, thank you all for your kind attention and any questions and comments. And I already can see some chat. So, all right. So double comment was, shouldn't there be a correspondence or equality between boundary? What sort of correspondence? Like correspondence between boundary of U complement and U? Because U complement can be very large. I mean, you can consider, for instance, like a torus, okay? So U can be inside completely U complement, like a torus. So then U complement might not have any boundary, whereas U can have boundary. Or you can consider two torus like this. So in general, there is not, but of course you can cook up situation where there are. Okay, Hawking-Bekenstein entropy in this picture. So I showed you some review article where they reproduce Hawking-Bekenstein using reduced Von-Neumann entanglement entropy, not using algebraic approach, rather more standard physics approaches. However, this is entirely not clear whether entanglement entropy and black hole entropy are exactly same. So one reason is that, yes, you can reproduce, at least for a scalar case, maybe for more general, I don't know. But there are some say caveat. For instance, Hawking-Bekenstein doesn't depend really if you take fermions or bosons or gauge field. On the other hand, entanglement entropy depends. So fermionic entanglement entropy is not same as Klein-Gordon entanglement entropy. Okay. So still it's not clear whether both are same. In algebraic approach, as far as known to me, people haven't computed it. But it's a really good project. And if any of youngster wants to do, it's a good thing. It's a very nice thing, actually. So the motivation of doing algebraic approach gives us more information like the area log something else. Yes. So you can motivate in several viewpoints. One is that for context of entanglement, I don't know how much I have been able, but at least if you just take this information, I mean, if you don't adopt this algebraic viewpoint, how can you really distinguish what is quantum mechanics and quantum field theory? Usually we tell, okay, one is finite degrees of freedom and is infinite degrees of freedom, which is true, loosely speaking. And then more precisely or more in technical words, or say if you want some very concrete characterization, tell me the difference. So you see, it's very sharp difference. The algebra is completely different. And I don't know in any other approach where you have such a sharp demarcation between quantum field theory and quantum mechanics. There are other motivations. So if you want to do quantum field theory, as you have done this beautiful lecture in this school, and again, thanks to the organizers for arranging such a beautiful school. You see, either in canonical quantization or path integral quantization, none of these are mathematically rigor. I give you some glimpse in canonical quantization. For path integral quantization, path integral measure doesn't exist in quantum field theory. So it doesn't mean that it will never exist. So far, no one has been able to show in fourth dimension path integral exists. Maybe it exists. Maybe people from measure theory will somehow discover a very enormous mathematical theory, and then everything okay. So far, it's not clear whether it is possible or not. Even this is not clear. But up to the say consensus is that so far no one has been able to do it. This is pursued in mathematical rigor way in the approach of constructive quantum field theory. So in lower dimension, like 2 dimension, they have constructed interacting model using path integral approach. This is so-called the Wiener measure has been constructed. But this only works even in lower dimension if you go to Euclidean signature. Now you could say, okay, if it works in Euclidean signature, we do weak rotation and then we have Lorentzian signature. This is true with some caveats which can be solved until you have a global time-like vector field, like a killing vector field, okay? Because you need time to do weak rotation. However, if you go to more general curve space-time, where you don't have a complete time-like vector field, then you don't have a notion of canonical notion of time flow. So what will you reflect back? So weak rotation doesn't work more than a stationary case. And there are situations where the weak rotation also doesn't give you whole information. For instance, if you take Green's operator, and if you do weak rotation, then if you do weak rotated wave operator, it becomes a Laplace operator, a Laplace type operator. And from mathematical side, this is called something elliptic operator. An elliptic operator will never have any singularity in some proper sense. On the other hand, wave operator have singularity, and this singularity propagates forever. There is no way you can kill this singularity. This is the UV singularity. And we know this singularity exists in quantum field theory. So weak rotation is not a bad idea when you really know why it is applicable. But if you just do everywhere, then sometimes you will miss something significant. So weak rotation doesn't work in general. And now you can argue that, okay, what works? And for linear or free theory, algebraic approach gives you the answer. Okay, now you say, okay, what about interacting picture? Okay, no one knows. So neither in algebraic approach nor in a standard physics approach, because Dyson series doesn't converge. Again, we don't know whether anyone will be able to solve this problem ever, but simply doesn't converge. Now in algebraic approach, you can show that in a sense of formal power series, it means that you go perturbatively order by order. and then every order is finite. That can be proven. This is somehow a generalization of the renormalization program that we know in our standard quantum field theory. But this also works in curved spacetime, at least globally hyperbolic case. So that gives you further motivation that if you adopt this algebraic viewpoint, then you can do at least certain thing in a mathematical better way. And sometimes not only mathematical better if you don't care about it, also physically, like for instance, entanglement. I don't care about mathematics, but if you just start from our physical idea, then it might be decisive. And one of the decisive things is that this infinite entanglement, that when you do brute force computation, we have encountered this. So there are several motivations, and it's up to you if you prefer one motivation over another. Next question is, Von-Neumann algebra is a polynomial algebra? In general, no. So a general Von-Neumann algebra may be very exotic object. It's not necessary to be a polynomial algebra. All right, so any further questions, comments?
I don't think I see any other questions. So if there are no further questions, maybe we can all just thank Onirban again for that nice and very clear talk.
Thank you, everyone. And thanks to the organizers for arranging such a beautiful school. I can only expect such thing exists when I was a student. And